Hello everyone, myself Sonia Rani. I am a research scholar in the Department of Physics at IIT Bhilai, and I will be your PMRF teaching assistant for this course Solar Photovoltaics Fundamentals, Technology and Application. So, I'll be taking a session per week on every Saturday at 4 p.m. And in that particular session, we will be solving some numerical problems to clarify your doubts regarding the concept of the topics. And please feel free to ask me anything at any point of time. You can just write a comment in the comment box, and I will make sure that I can resolve all the doubts of you. And so today's videos is for the dry run, and here we'll be solving some of the numericals from this week 0 assignment. Without any delay, let's start. So let me take this pen. So the first question is, FT statistic is applicable for. So here this FT is basically your Fermi-Dirac statistics. So it is asking that Fermi-Dirac statistics is applicable for which of the particle. So the first option is fermion, second option is boson, third option is photon, and the last one is none of the above. So for moving to this statistics distribution, the one thing we should know from these properties of this distribution is that these particles which are identical and indistinguishable with half integer spin follows the Fermi-Dirac statistics. So now what is this actually half integer spin means? So if the particle is having a odd multiple of 1 by 2 spin, that can be your 1 by 2, so 3 by 2, 5 by 2, 7 by 2 and so on. So that will be your half integer spin. And let's see what is the case in the case of boson. So bosons are the particles which have integral spin. So now by the integral spin, I mean it can be your 1, and it can be your 2, it can be your 3, and it can be your any integer value. So of course this is not satisfying this required condition for this spin for following the Fermi-Dirac statistics. So our second option will be eliminated from here. The third option is photon. So photon is actually an example of boson with a spin value 1. So again it is not satisfying this spin condition, that is half integer spin. So third option will also get eliminated here. Okay, so now the fermions. So fermions are actually the particle which are having half integer spin. So that means the fermions are having the spin value equals to 1 by 2, and this is the case which we want actually. So fermions are the particles which follow the Fermi-Dirac statistic. So for this question, your first option will be the correct answer. Now the second question is, the energy dependence of DOS for two-dimensional system. So here DOS is actually density of states. So it is asking you that the energy dependence of density of state for two-dimensional system is, means the density of states for two-dimensional system, it is proportional to the e raised to the power 3 by 2, e raised to the power 1 by 2, e raised to the power 1, or none of the above. So before moving to this two-dimensional case, the first thing that we should know is about what is actually density of state means. So density of states again tell you the number of states that are available in an energy level to be occupied by an electron. So for the case, for the two-dimensional case, if we are talking about, so the K space volume of a single state cube in K space is equal to pi by A multiplied by pi by B. Since we are talking here about the cube, so we can take A equal to B equal to L. So when we will replace the value of A and B with L, so that will give us pi square by L square. So it is the volume of single state cube. in K space. Now if we talk about the volume of sphere in two dimension, so in two dimension it will not having a sphere. What will be having? We will be having a circle. So basically here circle, for circle, so we will be having this pi k square. Again, to find out the number of field state, what we will do, we will divide the volume of the circle, entire circle which is available, with this volume of the single state, and we will also multiply it by 2, because since we are talking about electrons, so as we know that electron can be having spin up or down, so we have multiplied it by 2. Also to make sure that we are considering only a single electron, not the identical case we are replacing, so we have multiplied 1 by 2 two times, right? So when we will put the value of the V circle, that is pi k square here, and when divided by the volume of the single state, that is pi square L square, so on solving we will get the value of this N equal to k square L square divided by 2 pi, where k is a wave vector, or it is a having a value of square root 2 me divided by h cut. Now h cut is actually a constant, and its value is given by h cut equals to h divided by 2 pi, and where your h is the Planck's constant. So your h cut is h divided by 2 pi. So when we will substitute this value of k here in this expression, so we will get the value of n, which are the total number of field state. So that will be small m capital L square E divided by pi h cut square. So to find out the density of state, we represent it by using the symbol capital D, and it is obtained by doing a differentiation of this n with respect to E one time. So when we will differentiate this value of n with respect to E, we will get ml square divided by pi h cat square. Since here there is no E term present, so what we can do, just to represent it, we can also write e raised to the power 1, e raised to the power 0, sorry. So that value is actually 1. So for the case of two dimension, density of state is directly proportional to e raised to the power 0. So now let's check our option. So e raised to the power 3 by 2, it's not the correct answer. E raised to the power 1 by 2, again it's not the correct option. The third option is e raised to the power 1, but it is also not the correct answer. So e raised to the power 0, that is the case that we want, and since there is no option such given, so our correct answer will be the none of the following, that is your option number D. Okay, now the next question is, lignite, bituminous and anthracites are different types of nuclear fuel, coal, natural gas or biogas. So let's look a view at this picture shown here. So when the leaves or the organism get buried on the soil, so it is actually called as the peat, right? And under the application of pressure and heat over the time, this peat is converted into lignite, and that is finally converted into coal. Let's take a view at another image which is shown here. So in the starting that we have is the peat, which is due to the decomposition of the these leaves or the plants, and then finally due to the pressure it is get converted into lignite, and then with further application of heat with time it get converted into subbituminous, bituminous and anthracite. So you can see here the terms lignite, bituminous and the anthracite, that are actually the stage before converting it into the complete coal. So these are basically the different types of coal. So our option number second, that is coal, is the right answer for this question. Now the next question is, if the Fermi energy of any metal is 10 electron volt, what is the corresponding classical temperature? So here the Fermi energy of any metal is given, and it is asking you to calculate the classical temperature. Now to solve this numerical, what we need a relation which relates both the classical temperature and the Fermi energy of the metal. So here is the expression. So this 3 by 2 kT is equal to 3 by 5 of EF, and we will see it here like actually this 3 by 2 kT is nothing but the average energy, and it is represented by this symbol, and it is equivalent to 3 by 5 of EF, where K is your Boltzmann constant with a value of 1.38 into 10 raised to power minus 23 joule per Kelvin, and EF is the Fermi energy. So when we will solve it here, 3 will be cut by 3 here, and taking the rest of the term on the right hand side and leaving only the T, that is the temperature, classical temperature, on the left hand side, what we will have 2EF, that is your Fermi energy, divided by 5K. Now putting all the values here, since the energy here is given in electron volt and we want it in joule, we want to convert it in joule, so what we will do, we will multiply it by 1.6 into 10 raised to power minus 19. We'll put all the values, and after the calculating we get this T classical temperature value 4.64 into 10 raised to power 4 Kelvin. So out of these four options, your option number 1 is the correct answer, 4.64 into 10 raised to power 4 Kelvin. So thank you. This is all for the today's session. I hope you have understood the numerical problems. So thank you.